Is this on?
I believe so.
Okay.
Dan is going to make some announcements first, then I'll introduce you.
Yeah, the photographer just asked me to turn them up.
Okay. Might some compromise between the two.
No, okay.
Try this level.
Yeah.
It doesn't feel like anything happened at all then.
It's dimmed a bit.
I think you can start if you like. Most people are here.
Okay, before we start the afternoon program, a word from the sponsors, as they say. This is the Mathematics of Planet Earth Center for Doctoral Training. It's a joint venture between the Department of Mathematics at Imperial College and the School of Mathematics and Meteorology at the University of Reading. And we are very fortunate to have funding from both of these institutions, but we also are very fortunate to have funding from the EPSRC. And we have among us Catherine Moore, who is the representative of the EPSRC, so I would recommend to all the students to come and say thank you to Catherine for every possible opportunity that you have, because at least some of your funding comes from the EPSRC. We are going to have an award ceremony at the end of the afternoon, starting from 4:30, where our best and brightest students will receive awards. And we are very fortunate to have at least some of these awards sponsored by publishers, and we have sponsorship from Springer Verlag, and we will have with us Revi Lott, who is the editor of mathematics from Springer Verlag. We will also have sponsorship from Cambridge University Press, and we will have with us the editorial director, David Shona. And I believe David is not here because he is busy marking your posters next door. And also we have with us the editorial director of WSPC, Lauren Chaminette, who is here in the audience. And again, one of the prizes will be sponsored by WSPC. And we thank all the editors for their sponsorship. So for what follows next is we will have the oral presentations of the students, and I will let Colin run this. But the oral presentations of the students there will be a prize for the oral presentation of the students, and this prize is sponsored by Climate Kick, and we are very fortunate to have with us Alina Congreve, who is the representative of Climate Kick, and we have 3 students that are sponsored by Climate Kick among the 3 cohorts, and of course the students are invited to talk to Alina and do the same thing that they do, and they will do to Catherine, i.e. thank her. Okay, so Alina is in charge of choosing which one is the best presentation. So for the students, just make eye contact with Alina. Okay, I'm going to stop here and let the festivities begin. Thank you.
Okay, I'm just going to describe briefly what's going to happen for those of you who don't know much about MPCDT. So our students, when they come to us, they study in MRes for their first year. It's MRes in Mathematics of Planet Earth, which is a joint degree program between Imperial and Reading. And part of the training that students get in the MRes is in communications. So we have a communications expert, Justine Jones, who comes and does workshops with the students on Wednesdays. And part of that is focused in the sort of later part of the year is about sort of presentation skills. And one of the things that we like to focus on is the 3-minute thesis competition, which is something that's run, I think, internationally, where students try to describe their research in 3 minutes in a sort of publicisable way. And so all the students who are in cohort Charlie have been practicing their 3-minute talks, And so for the next 17 multiplied by 3 plus epsilon minutes, the students will introduce themselves one by one, and I'll just try to stand by and make sure that nothing goes wrong. And so I will introduce the first student, which is Adrian.
Actually, I'm going to introduce the whole cohort as well.
Ahead.
So yeah, we will manage the time. So we are cohort Charlie. I hope you enjoyed the posters just now for cohort Alpha and Bravos, and we are cohort Charlie to present some oral presentations on our projects. So we are in our MRes year, as Colin said, and we have just begun our research. Actually, we just started in January, and it's only around 10 weeks from now, and we do a whole range of research from weather to oceans, from theoretical stuff to computational, meteorological, or numerical stuff. In the following 3 times 16 plus epsilon minutes, we're going to give short talks. So no interruption, no questions, and at the end, if we have time left, we will have a short break, and feel free to talk to us after the talks. So I will begin myself. I'm Adrian, and I am working on the role of initial and model errors on uncertainty of weather forecasts. So let me start. Many people in this country love talking about the weather because it's one of the best observed yet unpredictable things. Imagine you're planning a barbecue next Monday. On Friday, you see the BBC's weather on the top panel. And the day after, on Saturday, you see the weather forecast for Monday here. And on Sunday, you see the bottom one. Like, ask yourself, how would you feel? Do you trust such a jumpy forecast? So some of you might have heard of the butterfly effect. That is when tiny errors become huge in some finite time. In the context of weather, that means any errors in our observed state of the atmosphere would contaminate our forecast rapidly. And likewise, any error in our model, which we have no perfect knowledge of, would ruin our forecast as well. And that's why there's a 2-week theoretical limit of weather forecast lead time. But 2 weeks is still quite far away. You see in this panel, you can't even confidently say about your weather in a few days' time. So motivated by this, I will take a step back and try to understand how the errors of the quality, how the errors would influence the quality of our weather forecast. So in my project, I use a slightly simplified model of the atmosphere. I'll play with introducing errors at different scales, some at large scales, some at small scales, and examine the error dynamics. So why is this important? Because modern forecasting techniques require ensembles, something called ensembles. And as the name suggests, it is a bunch of weather forecasts slightly different from each other. Today, many major forecasting centers, including the Met Office UK, make use of ensembles to gain more information of their weather forecasts. So to do this, they slightly change the observed state of the atmosphere and run the forecast, say 50 of them, and hoping that these forecasts reflect the uncertainties of the understanding of weather. So the results they get, so most notably the ensemble spread, would give them useful information on the confidence of particular weather events. So if we return to the barbecue example here, and suppose you know the ensemble spread. Say, among 50 ensemble members, most of them say it's going to be sunny on Monday, then you might just get ready for the barbecue. And if not, say, if it's going to be rainy, most of them say it's going to be rainy, then you might just call it off. But what if 20 of them say it's going to be sunny and 15 say cloudy and 15 say it's rain? So in this case, what you can confidently say is you're not confident about the weather. Yep, it is a bit counterintuitive, but this is the best information that we could tell from the ensemble spread, and this is actually very useful. The conclusion you make, however, is based on the assumption that you know the individual outputs of the ensemble members, and this is not reflected in our weather forecast now. So in that particular case, you can only see a sunny symbol on your smartphone app, BBC Weather. But that's somehow a misleading information, right? So some of you might want to think about how could the information of the ensemble spread be incorporated to the weather forecast delivered to the end users. And if you have some ideas, feel free to talk to me after all our talks. Thank you very much.
So my name is Christodoulos Sava, and I'll be talking about my project in the Embrace phase. So I'll be talking about atmospheric convection and Lorentz maps. So in numerical weather prediction, one area of research that's related with numerical weather prediction is the study of predictability, meaning that if we have a model to study what is how predictability is affected with that model, and first theoretically and then in terms of weather forecasting. So what is convection, first of all? Convection is a characteristic of the atmosphere that makes things complicated in terms of predictability. Convection actually is like the transfer of energy via mass motion. So one of the earliest simplified model for convection was the famous Lorentz 63 model. So you can see like the three equations that characterize the model on the top left image and right below the characteristic picture of it. So, and this model is used to study predictability. So, for example, if we see in the lower right image, we see that okay, if we start on different area of our model and we track our trajectory, we see that we may have like a bigger spread, meaning that lower predictability, or a smaller spread, higher predictability in terms of understanding where are we located and what's going on. So the crucial thing here is that since Lorentz's seminal work, there's been a huge development in the area of dynamical systems, and it's now known that we have a family actually of systems similar to Lorentz system, and a family of maps, functions associated with those systems, the Lorentz maps. So my project deals with the study of Lorentz maps, the study of the dynamical behavior, and be able to extract information related with the predictability in weather forecasting. Thank you for your time.
Hello to all and good evening. My name is Ioannis Katharopoulos and my research interests focus on meteorology and climatology. My MRS topic lies on glacial and interglacial cycles and stochastic resonance. In order to know the future climate, we need firstly to understand the past climate and the fluctuation that we had in the past. We have parallel climate data, which gives us insights in the past climate and the temperature profile and composition of the atmosphere. From this data set, we can see that we have a fluctuation between warm interglacial periods and glacial cold periods. And we have a periodicity between them of 100,000 years. What we don't know is we have a big gap of knowledge on why and how these transitions between warm and cold periods are made. So we will approach this problem with the usage of energy balance models. Firstly, to find the stable states of the atmosphere, and then to find the main feedbacks between the surface and the atmosphere. After, with the usage of stochastic resonance, we will try to find forcing that will reproduce the transition of the past climate. The framework of stochastic resonance is that if we have a dynamical system with many stable states, then and the noise which can force the climate, let's say the climate, to go from the one state to the other state, And then if we if we produce a small forcing, we can have fluctuations and periodically transition between these stable states. So our aim, our goal, is to find a physically realistic forcing that reproduces these fluctuations of the particle climate.
I've lost Matthew. There he is. Don the microphone.
Thank you. Such an honour. Hello, I'm Matthew and I'm here to talk to you about space weather. Most of you have probably never heard of space weather before and have no idea what it does and probably don't really care all that much. So I'm here to tell you what it is and why we should care. So space weather is defined as any sort of event or activity from the sun and the effect that it has on our atmosphere and basically life on Earth and also on our spacecraft, which we become more and more reliant upon as time goes on. So where does all this stuff come from and how do we get space weather? So the sun is at the center of our solar system. It's made of plasma, which is sort of a collection of charged particles, which when they move, they generate an electromagnetic field. Now, because the sun is a great big ball of fluid, as it rotates, the plasma towards the equator of the sun rotate faster than it does at the poles. So this has an effect of spinning around, creating lots of motion, which messes about with the field lines, the magnetic field lines. So when you have plasma in a pressurized condensed state, there's a theorem called frozen-in field, which means that they move the magnetic field with them, whereas if they're in an area of less pressure, so when it's away from the sun, they are constrained to the magnetic field themselves. So as the sun rotates, this messes up the magnetic field, and you end up with this great big ball of spaghetti of magnetic field lines. As they become all mixed up and pinched, that's when you can end up with something called magnetic reconnection, which is where areas of the magnetic field actually leave the sun. So these loops here show this. These are called coronal loops. So these are magnetic field lines that are broken free of the surface of the sun, and plasma still continues to run along them. So this is plasma spewing out into space. When this happens, they can reconnect, and this shoots a big ball of plasma out into the solar system at supersonic speeds, Mach 2, Mach 3, fires it out into the solar system. Obviously, we're out in the solar system, so if it comes towards us, it then has an effect on the Earth. Fortunately, we're protected by our magnetic field, which is generated by our iron core. Now, when it comes over to here, it can get caught in our magnetic field, and that's when it has effects on our ionosphere. It charges up the particles in there. This is what causes things like the northern and the southern lights. When you get really big coronal mass ejections, you get what is called a solar storm. So the largest one on record that we have so far was one in 1859. It was recognized by a British astronomer called Richard Carrington, and it is known as the Carrington event. During this time, it was noted that the northern lights reached as far south as Mexico and as far north as Cuba from the southern side of the poles. So it was seen pretty much almost everywhere on the globe, except if you were around the equator. It was said that the northern lights were so bright that you could stand outside in the middle of the night and read a newspaper by the light of it. At the time, the only technological advancements they really had in the 1850s was telegraph, and it was said that although they switched off the telegraph system, you could still send messages along the wire just by the amount of electricity that's in the atmosphere. In 1989, there was another magnetic storm which hit Earth, nowhere quite as big as the Carrington event, but it was still quite strong. This one had effects down as far as parts of Canada, to put things into perspective that way. But because we now have an electrical network, we have a power network, we all use electricity in our homes, the amount of power that surged through the system was enough to melt one of the power transformers. So it has been estimated by Lloyd's, in fact, that if a solar storm on the scale of the current event was to happen today, the amount of damage could be up in the trillions of dollars purely because it would take out our electrical system, which would leave millions and millions of people all without power for weeks on end while they go around to try and fix it all. So what we are trying to do is come up with a mathematical model so that you can, if you can sense one of the coronal mass ejections happening, you've got a gap of about 22 hours-ish before the plasma gets to Earth. If you can determine how strong that coronal mass ejection is and what effect it can have on the Earth, you can then send out warnings to the areas that will be affected so they can at least turn off the power grid before it happens. You're going to get blackouts anyway, but at least if you do that, you can turn it all back on again once the danger's passed. Thank you all very much for listening.
Julia.
Thank you.
Congratulations.
Hi, I'm Julia, and I'm interested in what broke this camel's back. Well, we know what it is actually. It was a little straw. So a little change or a little action that has an unpredictable and large reaction instead. So great shifts like this can be witnessed, for example, in the dynamic of population when we have mass extinctions, or in economy when a microcredit can help to get out of the poverty trap a large amount of people. But we saw these things also in the climate of our planet. And for example, 55 million years ago, a sudden release of methane from marine sediments triggered a positive feedback of global warming, and our Arctic became a 23 degrees freshwater pool. Maybe it might be difficult to get back to 55 million years ago, but we could easily go 7 years back from now. So in 2010, Russia experienced very dry and hot summers, and this caused severe wildfires, and in particular peatland wildfire. Peatlands are estimated to contain as much carbon as the atmosphere itself. So if the temperatures continue increases, that could trigger this compost bomb instability and release a lot of carbon in the atmosphere. So a fast change in the parameters are leading to a massive critical transition, passage to a tipping point in our system. So we're interested in, I'm interested in understand these tipping points, and in particular try to have some early warning indicators so that might help us predict this tipping points. And models at the moment, they show some delays in the early warning indicator when the tipping point is due to a fast change in the parameter. And we can witness these problems also in models that has noise in the model, so they are a bit perturbed. And these models usually, they have noise that has a mathematically convenient hypothesis, but a bit restrictive physical hypothesis on it. So I would like to have some more physical reasonable constraints on the noise, and investigate the tipping points in general and early warning indicators in particular to help the camel understand when he had to call the doctor for his back. Thank you.
Thank you. This is so weird. Yeah, so for those of you who don't know me, I'm Maria, and what I want to do for the next 3 minutes or so is talk about why I chose the project that I did and why we care about it. So I don't know when the last time you guys had a blackout, but the last major blackouts in British history occurred around the political unrest of the 1970s. And while they don't happen as often anymore, and they probably won't happen that often in the future, they really are worst case scenarios for energy distributors. And mathematically speaking, they are extreme events that that happen rarely but have high impact and cause huge disruption. So what I want to do is look at these extreme events in the case of electricity demand. And I want to use extreme value theory to do that. So extreme value theory allows us to answer questions such as, what is the probability that some demand in the future is larger than any past demand that we've ever had? What is the probability that future electricity demand is going to be larger than some threshold that is already quite high? And then if it does exceed that threshold, by how much more? And also what I want to do is, can we estimate the upper limit from any one household or any one business about what is the maximum demand? And can I put some confidence bounds on those? And in addition to that, I also want to put in factors about how society is changing and about how environment is changing. So people might get solar panels, or they might buy more electric vehicles, but also the climate is changing, and etc. And this is particularly useful for both for policymakers and for industry, because it allows energy distributors to incentivize people to spread their consumption over more of the day so that peaks don't occur as often, and when they do, their magnitudes are lower. And also that we can perhaps invest in grid development, and we can decide better how much to develop it by. So this is what I want to look at, and if you want to know more, please come talk to me after. Thank you.
Sure, I can reach up to you. There we go.
Thank you. How's it going? My name's Kevin. Now, the ocean stores a vast amount of CO2, yeah? And this ocean is in contact with the atmosphere. And it is estimated that the ocean absorbs 27% of all CO2 emitted by humans. So I'm talking about fossil fuels, changes in land use, etc. Furthermore, it's estimated that 30% of all CO2 emitted by humans since the Industrial Revolution has been absorbed by the ocean. So the ocean is hugely important. And knowing this absorption rate is key, because it will co-determine our climate's future, and also it changes the ocean chemistry. So this is an increase in pH, which affects marine biology, marine organisms, and biodiversity. So to know the flux, or know the absorption in the ocean, we need to know the CO2 concentration on the ocean. And this is what I want to do. And to do that, it's done using Gaussian fields and Gaussian Markov random fields. But let's ignore the jargon now for a while and call it Jerry. And this is Jerry, my robot Jerry here. And Jerry, he's got this hand that moves in this random motion. But we can tweak Jerry so that this random motion is smooth. And what I'm going to say to Jerry is, Jerry, start from Ireland. I'm going to stick a long roll of toilet paper in Jerry's hand, and I'm going to run Jerry across the Atlantic. So Jerry runs across the Atlantic with his random arm, moving the toilet paper up and down, where the height of the toilet paper represents the concentration of CO2. Now, Jerry's arm is completely random, so he's going to get this wrong. Straight away, he's going to get this wrong. But I'm going to say, Jerry, do it again. So Jerry's going to run across the Atlantic Ocean again and create another roll of toilet paper. And I'm going to tell him, do this again and again and again. And eventually he's going to cover the ocean with 1 million rolls of toilet paper. And what I'm going to say, we have this data. And this data is very sparse in both time and space. And I'm going to say, Jerry, pick only the toilet paper rolls that cross through data points. Yeah? So then I'm going to have a subset of toilet rolls that cross through these measurements of CO2 concentration. And from this subset of toilet rolls, I'll be able to measure an average CO2 concentration and also an uncertainty. And then from that, I'll be able to know the CO2 concentration across the whole ocean. And from that, get an idea of what the absorption rate is. Thank you very much.
Cheers.
You got something to tell us?
Oh, yeah. All right. Maybe I should go on this side. Oh, how can I top that? All right. So hello. The world is getting warmer. The UN's Intergovernmental Panel on Climate Change, or IPCC, reported in 2014 that it is extremely likely that human influence has been the dominant cause of the observed warming since the mid-20th century. Now, in response to this, scientists run computer models of the climate in order to make predictions that we can either mitigate or prepare for. But in order to run an accurate model, we need to be able to understand the motions in the atmosphere and the ocean. Now, fluid motions in the atmosphere and the ocean are inherently unstable. And being unstable means that particular small changes to the flow can grow exponentially. A particular type of instability, called baroclinic instability, is what gives rise to storms and weather systems in the atmosphere. Now, baroclinic instabilities are also ubiquitous in the ocean, and so the ocean has its own weather, its own oceanic storms. Let's see what I did there. Now, baroclinic instabilities naturally arise due to the temperature gradient between the equator and the poles on the Earth. And if you imagine heating the bottom of a pan full of water, the vertical temperature gradient you set up drives convective overturning motions in the vertical plane. Now, in a similar way, the horizontal temperature gradient between the equator and the poles drives convective motions in the horizontal plane, giving rise to these eddies. Now, the ocean is a crucial component of the Earth's climate system. It continuously transports heat away from the equator and towards higher latitudes. Now, without this heat transport, the UK would be far colder than it is otherwise. And oceanic storms, or eddies, are important to understand as they transport anomalously warm or cool water along with them. However, they're currently not well represented in climate models. I'm currently looking at a different mathematical way of understanding baroclinic instability, looking at the motions of fluid parcels within these oceanic storms. And I will also be analyzing data from an ocean circulation model from MIT in the light of this new mathematical framework. Now, the motivation is that the better an understanding we have of oceanic eddies, the better we can implement them in climate models. And the better implemented they are, the more accurate the predictions from those models will be. And ultimately, the more accurate our predictions, the better we can be prepared for the future. Thank you.
Hi. We know that there are huge amounts of plastic in our ocean. It is estimated that about 8 million tons of plastic enter the ocean every year. And this is causing enormous problems to marine life, the environment, and humans too. Plastic destroys coastal habitats, plastic kills animals, and plastic ends up in the food we eat. Most of the plastic litter enters the ocean directly from the coast all over the world. Due to the ocean currents, large amount of floating plastic ends up in one of the 5 large spiraling ocean circulations, the so-called ocean gyres. The circular motion of these gyres, that is driven by the wind and the rotation of the Earth, pushes the water steadily to the center of the gyres, where after many loops around the basin, the water finally sinks down, flowing out in deeper water. The plastic, however, doesn't sink, so it accumulates in the center of the gyres, in the middle. So the largest accumulation of plastic is in the North Pacific Ocean Gyre, or also called Great Pacific Garbage Patch. The size of this plastic soup is estimated to be about 7 times the size of the UK, and it is constantly growing. It is, however, not as simple as that. In fact, there is much more going on than the large-scale circulations. Much is driven by the oceanic weather that Peter was talking about, that can have a large impact on the plastic movement in the oceans. So in my research, I will be looking at the case of 2 large-scale circulations, 2 ocean gyres, with flows in different directions. So that gives rise to turbulence and mixing at their interface. So we can predict this complicated behavior, and with enough computer power, we can actually draw very detailed maps of oceanic weather, as the one you can see on the slide behind me, which was done by NASA. But so far, we know very little about the effect it has on the movement of plastic particles. So I will use computer simulations to investigate whether plastics can cross the boundary from one circulation to another one, ending up in a completely different part of the world. Also, I am interested in whether the size and the shape of the plastic particles make a difference in where they finally end up. So this is one project in a large group of ongoing research on the movement of plastic particles. But I hope it will help us understanding where all the plastic ends up so we can target plastic litter properly. Thank you.
Thank you. There we go. Hello, I'm Ben. So, how can we improve the tracking of plastic in our oceans? Following it on. Plastic, like many other things, can be thought of as particles in maths. Now, particle tracking is of great importance to oceanographers. We can study the roots and the behaviour of plastic in our oceans, which is a real problem, as we've already heard. But we can also think of looking at smaller particles like pollutants and model how they move and mix in our oceans and maybe gain a better understanding for how they might interact with other marine life. And we can even go as far as thinking of marine life and modelling tuna populations, for example, using particle tracking software. The issue here, though, is in how do we solve these problems numerically. Now, particles are very different from fields. Fields being things like the velocity of the ocean flow or the temperature of the ocean. My project is mainly about coupling together two pieces of software. One called FireDrake, which we've already heard about today, that can efficiently and robustly solve for the fields. And the other called Parcels, which has been created to specifically handle the particle tracking aspect of things, but has some limitations. One example being that it can't handle any data from about 40 degrees north latitude and above, which includes the UK. So looking so the next step, logically, once we have our coupled software, is to look at some real data and some real problems. So we can look at plastic pollution and how it propagates using data from the UK coastal zone. We can also build upon the idea of coupling together fields and particles in a more general sense, for example, for climate data problems as well. So in summary, we can track ocean plastic using particle tracking software as just one example of something we can model using particle tracking software, and it's my project to help improve its capability. Thank you.
Another tall person.
Thank you. Thank you. So you've just heard about tracking plastic in the world's oceans, and my name's Joe. I'm going to talk about tracking something a little bit different, which is tsunamis. Now, tsunamis can travel at 200 meters per second. That's 20 times faster than Usain Bolt. So time is of the essence when we're looking at a tsunami problem. As I'm sure you all remember, in 2004, the tsunami which struck on Boxing Day was absolutely disastrous, and it was in fact the most disastrous tsunami that's ever recorded, killing 250,000 people. So surely we want to avoid such a tragedy ever happening again. One strategy of doing this is to improve the early warning system that already exists, in the Indian Ocean, to make it as good as the ones that already exist in the Pacific and the Atlantic. But then in 2011, we saw that the one in the Pacific isn't so perfect either. And the more or less unpredicted tsunami, well, not unpredicted, but not sufficiently predicted enough in tsunami that struck in Fukushima, caused a disastrous nuclear meltdown, which is still it's not even started being cleared up today. So surely with the advent of modern computer technology, there must be some solution. In the world of computer technology, the energy required to run an algorithm is approximately proportional to the so-called computational cost. Now, as the saying goes, time is money, and therefore by reducing the energy required, we reduce the cost, and therefore we make a quicker algorithm. One way to reduce the energy is to use the process of adaptivity. So what this does is it focuses the computational power on important locations, such as the tsunami and the coastal regions where we want to protect, essentially we want to evacuate, and it saves energy by not focusing elsewhere, by reducing the cost elsewhere. The way it does this mathematically is because of course we solve this problem over a mesh, we used more mesh points at the tsunami and on the coast, resolving them as accurately as we need, but then having fewer points elsewhere, given the coarser mesh, and using less energy. But not only does this mesh vary spatially, as you can see here, but it varies temporally. So as the wave moves along, the mesh essentially follows it, chasing the waves and leaving coarse mesh in its wake. So as I said at the start of the talk, tsunamis can travel at 200 meters per second. That means they can cross the entire Indian Ocean in just 2 hours. So time is of the essence, but accuracy is still important. The word tsunami comes from the Japanese, where tsu refers to a sea wave, and nami refers to harbour. So hopefully, by embracing the technology provided by adaptivity, we can stop any tsunamis causing such wreckage in harbours of the world in the future. Thank you.
It's a very low one.
Okay, I'm Golo, and I'm working on asymptotic limit analysis for finite element methods. Now, 2 examples of weather events are typhoons and thunderstorms. And while thunderstorms are more of a local event, typhoons are large-scale events that can range over many hundred kilometers. Now, that includes that the horizontal range is much bigger than the vertical range, which is the height of the atmosphere. Now, from a mathematical point of view, that means that we can make a simplification in the underlying dynamical equations that describe the atmosphere. And that is, we simply say that the rate of change of vertical velocity is comparably small to the other terms in the equation, such as gravitational force. So what we then do is we just delete the vertical acceleration term and use that. And it turns out that this simplification, which is called hydrostatic approximation, is good to use for large-scale weather forecasts, such as for forecasting typhoons. However, if it comes to more local events, such as a thunderstorm, then that's not so useful because there's lots of upwind and downwind going on, and we can't ignore the rate of change of vertical wind, so that doesn't work so well. Now, currently, the Met Office is developing a new dynamical core, which is a numerical setup to solve a set of underlying physical equations for the atmosphere. And they're trying to use what's called a finite element method to numerically solve these equations. And as with every numerical method, what one has to do is to check if that's a good method and if it comes up with the right sort of prediction. And one way to do this is to apply it first to a simpler set of equations. For example, a simple set of hydrostatic equations. And that's what I'm doing at the moment. I'm trying to set up a finite element frame for a set of hydrostatic equations and see how the finite element method behaves there. And once that's achieved, once I get good results in that respect, I then turn to the non-hydrostatic case, i.e. the case where there's a rate of change of vertical wind. And what I do then is then I apply this framework for this non-hydrostatic case, but in that case it's a lot more difficult to say if it's behaving well because the situation is a lot more complicated. So what one can do then to check if it's still working well is one can sort of slightly decrease the influence of the rate of change of vertical velocity until we are back to the hydrostatic case. And what we would then expect is that the predictions for the non-hydrostatic case slowly go back in the right sort of way to the hydrostatic prediction. And if that's the case, then we can say that's a sensible numerical framework. And that's what I'm working on. Thank you.
Hi everyone, I'm Laura, and my research is on separating the climate from the weather. You may have noticed in weather forecasts that there are often wave patterns in the wind and pressure levels, particularly over the UK. These are important to us because they carry with them the good and bad weather, so they're key for understanding how our weather will change. The first step to understanding these waves is we need to know what they are lying on top of. You may find it difficult to analyse water waves in a tank if you don't know the height of the water. And similarly, it's difficult to analyse waves in the atmosphere unless you know what the atmosphere is doing underneath. So, we want to separate the atmosphere into two parts. First, the underlying layer, which is the climate. That is how we see the atmosphere to behave over long periods of time. So this should be quite smooth and stay constant for years to decades. Then, on top of this, we have the weather. So that is the part of the atmosphere that changes quickly, and that is what creates the waves. So we basically need to split the atmosphere, into the constant climate and the quickly changing weather. Now, how would we do this? One method is to take an average over all longitudes to obtain your background, which would what you would call the climate. But we find that this isn't consistent with our definition of the climate because it doesn't stay constant in time. So we are looking for a new approach. I will be trying to use some physical properties to be able to isolate the climate and the weather in a better way. I will be assuming that the mass of air in the atmosphere and in the climate are the same. So that means that the weather isn't adding any mass to the system, it's just moving it all around. Then I will also assume that the climate is a minimum energy state. That is because without any waves, it will do the easiest thing possible. Think again of the water in the tank. Without the waves, the water will fall flat. So using these properties, I hope to be able to isolate the climate and the weather, which will be useful for people who are studying the climate and people who are studying the weather. And it will also be key for people who are looking at the interaction between them. So how will our weather change in response to the future warming climate, which is something that we need to answer with increasing urgency. Thank you for listening.
Thank you.
Okay.
Heard that. Hi guys, my name's Imogen and my MRes project concerns intimate relationships in the atmosphere. Our planet's atmosphere is made up of layers, and for a long time scientists assumed the lowermost layer, the troposphere, to be the sole driver in our weather and climate. However, in recent years, scientists have begun to realize that there's an intimate relationship between the troposphere and the region above it, the stratosphere. That is, we now know what happens in the stratosphere influences what happens in the troposphere, which in turn drives our weather and climate. There exists an equation to represent motion in the stratosphere, and despite being born out of approximations, it actually does a really good job of telling us what's happening up there, up to 50 kilometers above our heads. There is, however, one problem, and that's where my research comes in. There is a single line in the stratosphere where the equation does not work, the so-called critical point. As a consequence, we have no idea what's happening there. And to resolve this, we need to zoom in on that line and take a close look in a thin region above the line and a thin region below the line, the so-called critical layer. So what is happening here? Well, as it turns out, waves are being generated here and spreading out throughout the stratosphere. Why do we care? Well, it comes back to that intimate relationship between the stratosphere and the troposphere. These generated waves represent changes in the stratosphere, which in turn cause changes in the troposphere. These changes in the troposphere consequently cause changes in the stratosphere. So you see that one affects the other and the other affects the first. Once we can create a mathematical framework for this highly delicate relationship, we'll be able to say more about the transport of greenhouse gases and predict the movement of, say, volcanic aerosols following an eruption. We'll also be able to quantify the effects of ozone depletion on the atmosphere and get better at predicting month-to-month and year-to-year variability in our weather and climate. Thank you.
Hi, my name is Ivis and I will try to make sense of this particular title here. So you can imagine, we can start by having a guy in a fairly large city that has only two actual sort of layers of roads, just roads that run parallel to each other and perpendicular to each other. And our guy moves through the city. He flips a four-sided Dungeons & Dragons dice, and he chooses at each intersection which way he's going to follow.
And then he paints actually his way through the city. Now, we can actually make it a bit more complicated, and at this intersection we create a magical ladder upwards and downwards. So we have a multi-layered city. We take our 4-sided dice from the guy and give him a 6-sided dice. And then he again paints his way through the city. Now, that's all fair and nice, but we can actually now even remove the guy and place a water molecule in his place. And we can moreover zoom out of our multi-layer city. And we sort of, in a sense, have a nice network, but it still doesn't tell us a lot. Now, we can place more water molecules and sort of form a water cluster. Now, again, not much to say here, but we can also now move that water cluster and place it inside the rock matrix. And then we again have our paths, but actually we now have something even more than our paths. We have a boundary around our paths, and that boundary separates the water molecules, or the entirety of the water contained in our rock matrix, from the rock matrix itself. And it turns out actually that in most cases where we simply simulate how water moves through a rock matrix just by solving the equation at each little pore of the rock, we can instead now just not even simulate its curve independently. We can just simulate the boundary, and through some very nice properties which I'm going to explore through my project, we can actually make sense of the entire movement of the flow through the porous media just from that boundary. Now, again, it might seem that the boundary is actually not any simpler than the curves themselves, but we can do something even more. We can actually transform that boundary into something even simpler and reduce our calculation time even more. Now, that's just one application. We can go into a step further and actually model forest fires. Now, through forest fires, we can place a small arsonist somewhere in the forest, and not through regular media. Don't ask me about the particular example. It's some very specific example, but now we can model actually the forest fire as a process where the boundary is the boundary between burned and non-burned trees. And we don't even need to know, again, every simple path that the fire has transversed. We can just draw the boundary, take some nice properties from the boundary, simplify it, transform it into something we know how to solve, and actually model how the fire propagates to a certain forest. And that would be it about my project. Thank you.
And I think this is the last talk, if I've counted correctly. That's correct.
1, 2, 3 testing, 1729. Okay. Hi. So my name is Marco, and before I start, I've got a little question to ask. Has anyone here seen the movie Frozen? Yes. Oh. What's it like? Because I've never seen it, but it raises an interesting question, and that is, how is it that we all love snowflakes so much, and yet we spend so little time thinking about how snowflakes grow? Now, I don't actually blame you if you don't spend much time thinking about this problem, because as it turns out, one equation which has been proposed as a model for snowflake growth, the KPZ equation, is pretty scary to work with. It involves something which locally resembles Brownian motion, which gets differentiated and then squared. You know, to call it scary is a bit like calling the Titanic an unpleasant vacation. Now, up until a few years ago, mathematicians could have, speculated about how to make rigorous sense of this equation, but it would have been a bit like me thinking of a list of things to say on my third date with Beyoncé. Like, realistically, it wasn't going to happen. But then it did. Martin Heidegger came along pretty much out of the blue with a theory of regularity structures, which is a generalization, can be thought of as a generalization of rough path theory, which allowed for the KPZ equation to be solved. And you're probably thinking, great, so now what? Why should I care about the KPZ equation? Well, as we all know, clouds and snowflakes do affect the weather, and so having better models for them could allow for better weather predictions and climate models. So that's one reason why you should care. The second reason you should care is that snowflakes are just awesome. We all love them. So in summary, that's what my project is about. using regularity structures to approximate solutions to the KPZ equation and verify that this equation does indeed make a good model for cloud cover and snowflake surface growth. So that's it from me. That's it from MPE CDT cohort Charlie. Thank you, London. You've been a fantastic audience. Good night.